Sorry. All right. So I just started the recording. I'm sorry if y'all are going to go back on this, but you don't care, do you? You're here. Right. Okay. What was that? Exam 2? All right, let's look at exam 3. This is what work and energy and momentum on exam 3. Have I given away anything on the exam? What have I told y'all? You're going to have 2D problems. Huh? I know. What else did I tell you? You're going to have an estimation problem, right? What else did I tell you? Like the coffee cup? You're going to have, huh?
Graphical analysis.
You have to do graphical analysis, like where the graphs, you have to translate between position versus time and velocity versus time. Anything else? I think that was about it.
One where you had the kilograms meters squared over.
Oh yeah, where you're calculating R in exam 1. Sig figs. Yeah, let me, just for the people that are watching the recording. Okay, this will be a good review for y'all too. So you're going to have one like this where you have to find R. You're going to have one like this where you have to find the volume, estimate the volume of something. You're going to have, what else did I say for sure? Oh, you're going to have one like one of these where you're, did I say the sugar cube?
One like that where you got to do the millimeters or this.
Yeah, like the sugar cube. Like that one. You're going to have to analyze graphs. I mean, that you should know that you're going to have to analyze graphs because there are so many of them. You're going to have a 2D problem like number 18 or like the one on the free response. I said you're going to have to do a vector problem like that. These shouldn't be big surprises to you. Like, you're not surprised to hear these things, right? Yeah. I think that's all that I told you. I told you to make sure that you're reviewing sort of what projectile motion is, and that you will also have a projectile motion problem, like one of those 3. And that you will have a 2D problem. Yeah, I think that was all that I gave away. Right, that was it? I think so. All right. Sorry about that. So, exam 3. Oh, I think I also told you that you would not have a centripetal force problem like that. Okay, exam 3. What do you want to look at? Work and energy. Numbers 1 and 2. Work energy theorem. That follows over into 3. Number 5 is a conservation of energy problem. You can work it with kinematics too, but it's easier with energy. Want to look at any of those? Number 1. Okay, so a 10 kilogram kid comes down a slide. The slide is 3 meters high and 5 meters long. Some of you just got confused with the numbers, I think, but it would have helped you if you just drew a picture. It's 3 meters high and 5 meters long. And I have this kid up here, and he goes down the slide, and there's a frictional force of 10 newtons that acts along the entire length of the slide. So the work done by friction is the friction times the distance. That's 10 newtons times 5 meters. So that means that that frictional force does 50 joules of work. Now, the energy that he has at the top is equal to mgh, which is 10 times 10 times 3, 10 kilograms, 10 meters per second squared, times 3 meters, so that's 300 joules. So he has 300 joules at the top. The frictional force takes away 50 joules, so at the bottom he has 250 joules. And all of that energy is in kinetic energy, 1/2 mv squared. And so, so here I was just looking for the work done by friction. So that was the answer there. But if I also wanted to know the velocity of the kid at the end, then I could do that too. Half of m is 5. So v is equal to 5 meters per second. Because 250 divided by 5, oh no, square root of 50. Should be square root of 50, which is about 7 meters per second. 250 divided by 5 is 50, and then so I took the square root of 50, so it's 7. I could change that problem in that way. That would still be the same problem in my mind. Would it be the same problem in your mind? The same ideas, like they're the same stuff going on in that problem. I don't know that I did, but I could. There are 9 questions from each exam. I think one of them I might have trimmed a couple away, but it's pretty much equally distributed between each exam. All right. Energy right here, there was a free response too. That's just doing the kinetic and potential energy. It should be always equal. Y'all holler out if you want me to do something. This is potential energy. Power is work over time.
Number 8.
And number 8, yeah, so this was just like the conservation of energy problems. It is a conservation of energy problem, except now we're dealing with elastic potential energy. And so I have this spring, and it shoots a ball straight up. It's like a spring-loaded gun, right? And it goes up 5 meters. Down here, it has elastic potential energy. Up here, it has gravitational potential energy. I know those two have to be equal. So PES equals PE gravitational. That's 1/2 kx squared equals mgh. So that's 1/2 of 250. That's this number times x. That's what I'm looking for. Is equal to the mass 0.02 times 10 times h, which is 5. And so x is equal to the square root of 1 over 125. Uh, 0.089 meters. But because that's such a small number, it's easy to represent in centimeters. So remember to convert to centimeters, really easy. Boop, boop. 2 places over for meters to centimeters. Or you can do the whole thing, divide by 100. Okay? Cool. All right. This is a momentum problem. It's like a collision. There are similar ones. Oh, there's a similar one in the free response. The total momentum has to always be 0, or it has to always be constant. This is a Newton's second law, F equals delta P over delta T. Watch your signs. And then we get into rotation. Remember, nothing like 14 on there. It's a kinematics problem. Y'all holler out if you want to do one of these. Number 15. Okay, fan is switched on. These are really, really similar to chapter 2. So you just want to start writing what we know. First of all, the fan is switched on. That means that V0 is equal to 0, and it has an angular acceleration, alpha, equal to 30. Okay, I know that's positive because it's speeding up in the same direction. So the alpha and the velocity are the same. I want to know what is omega after t equal 4 seconds. So omega, oh, this should have been omega naught, not v naught, I'm sorry. Omega is omega naught plus alpha t. Oh, so this is just 0 plus 30 times 4, 120 radians per second. All right, some of your kinematics problems, if you have them, you'll have them, will be simple like that. Others are not as simple, but not impossible, just an extra step or so. All right, torques. You had a couple different problems on torques in your exam, so you'll probably have to do that. Any of these? Cool. All right, let's look at exam 4. Exam 4. Why do y'all miss this number 1? It's one of the heavily more missed questions. It's not hard there. The energy is 1/2 mv squared plus 1/2 I omega squared. The only hard part is you have to figure out what I and omega are. I for a hoop is mr squared. Omega is equal to v divided by r. Both those are in your equation sheet. This equation was v equals omega times r. And then I just solve it for omega. And so I do that to put into here and here. I think in this case it was 40 plus 40 or 80. Number 3, I just like these problems. I love ranking problems. So you'll have one like number 3 where I give you a shape. It's a shape you've never seen before. And I ask you to rank the momenta, the moments of inertia. You're looking for a couple of tricks. First of all, usually there are 2 points that are identical. Like here, B and D were identical. So that gets rid of A and D, because it doesn't list B and D equal to one another. So just, go by, eliminate those immediately. And then I also like to look for the one that gives me, obviously, the smallest moment of inertia. And in this case, that's A. The reason A gives you the smallest moment of inertia is because it decreases R for every point. And R is like the big gorilla. Like if you increase R, that increases your moment of inertia by a lot. So if I do that with A as the smallest, that means the answer has to be B. And D is the biggest moment of inertia because, look, from point D, that's as far away as I can get from the other side of the star. So that makes the moment of inertia biggest around point D. Okay? That would be like rotating about this point. That's really hard, right? You ever seen somebody rotate about this point? Yeah, you do, but you say, wow, because that's difficult. Okay. Any of these stand out to y'all? This is all fresher, I think, for you, right? These you want me to work? Make sure you know all your principles. Like number 9, there are other questions like this, but number 9, that's for Archimedes principle, but I could easily make it any other principle. So make sure you know what these are. They're all listed here. This is, which one is this? That's Pascal's. This is Archimedes. That was the answer. This is Bernoulli's, and this is Newton's second law. So make sure you know all those principles. There was another one we did, right? What was that? Oh, yeah, continuity equation. Yeah. Any of these folks? Yeah. Look.
Oh, yeah.
Okay, yeah, so what happens? The first thing that happens is your volume increases. You usually get bigger when you take a big deep breath of air. So the volume of your body increases. And because the volume increases, the buoyant force increases. Right? Because buoyant force is equal to the density of the fluid, the volume of the object, times G. And since this goes up, this goes up. That's why when you take a big deep breath, you float, because your volume increases. Your apparent weight decreases. Remember, apparent weight is the difference between the weight and the buoyant force. And since the buoyant force goes up, that means your apparent weight decreases. You feel lighter when you take a big deep breath of air. That's why you float up in the pool. And the average density of your body increases. Well, density is mass over volume. And so if your volume goes up, that means that this actually goes down, right? Less dense things float, so that's not correct. So 1, 2, and 3. Follow? Lucas, is that good? Any of these others? Okay. How about here?
Number 11.
Number 11. Okay, so this had to do with both our pressure measurements. Remember, our pressure measurements, P is equal to rho GH. So the point is that P and H are related. That the bigger H is, the bigger P is. Also notice here that P is not dependent upon the diameter of the tube. It's only dependent on the density and the height of the column. So, like for example, if you change the fluid, if you make it mercury or some other fluid, then that changes the height for a given pressure. Anyway, here I'm only worried about H. And so the one where the level is highest is where the pressure is highest. So I want to find the point where the pressure is highest. So then two different principles come in play, the continuity equation and the Bernoulli's principle. Continuity equation would tell me that I have a small velocity here and a big velocity here. That's from the continuity equation, A1, V1, that has to be constant. And so if A goes up, that means V goes down. So here I have big A, small v. Here I have small a, big V. And then the Bernoulli's principle says if V is big, the pressure is decreased. So I have a big velocity here, I have a small pressure, and here I have a big pressure. So my standpipe is going to be full up to the top here, but it's going to be small right here. So this level of the fluid is highest at A in that standpipe. It's a good way to measure pressures for pipes. They do that actually. So I have a big pressure here, small velocity, big pressure, big velocity, small pressure. All right. Oops. And these others, y'all? Nobody got 20, right? Do y'all like Speech 101? Let me be honest with you. Do you like it? Like Speech 101? Okay. It was okay. All right. Huh?
I haven't taken it yet.
Oh, okay. It's awkward. Yeah, I made my Speech 101 instructor cry in class. And then I dropped it, and then I went to like the provost, and I was like, I don't have to take this class. And I was like the one student in Mississippi that year that didn't have to take Speech 101. They just waived it for me. I used to be kind of mean. Like I know I'm mean sometimes now, but back then I was mean a lot. Okay? Is that all? I'm really sorry for the recording. What you gonna do? Okay? But I'll still give extra credit for those not here. All right, don't leave. I'll need to